Okay, let's start. It's a pleasure to welcome Professor Debora Sijacki from IOA Cambridge. Debora did her PhD from the Max Planck Institute for Astrophysics in Garching, and then mainly with Volker Springel and Simon White. And then she moved to IOA for a postdoc there, for a first postdoc, and then she did a Hubble Fellowship here at the CFA from 2010 to 2012, before moving back to the IOA as a university lecturer for 3 years, and now she's a reader in astrophysics there. She's an expert in cosmological structure formation, and she has mainly worked on AGN feedback models and cosmological simulations. And today she will talk about galaxy formation simulations, substrate versus physics.
Thanks very much, Rahul. So it's a real, it's a real pleasure to be here back at CFA. It always brings back happy memories and times of really exciting and productive work that we do together with Lars and many other great people that helped some of the science that we wanted to get along during those years. So I also have to make an apology. I got a really bad cold and my voice is almost gone. So if you cannot hear me in the back, please say, I'll try to shout more, but it might not be possible. So today...
All these empty seats, there's no space. You should just move forward.
Thanks, Ramesh. So in this talk, I want to tell you a little bit of a kind of critical review about the galaxy formation simulations. I want to tell you some of the great successes of these simulations, where this field stands, and I want to tell you some of the really big challenges that we are facing ahead and trying to push this field forward. So I'm making a little bit of an intro because it's a colloquium after all, even though probably you're all experts in this. So bear with me for a moment. So I just want to tell you a little bit what cosmological simulations of galaxy structure formation are and why they are such a useful and great tool. So essentially, our ultimate goal, and we are not there yet, is to provide ab initio physical understanding of structure formation on all scales. And that's where we are striving at. Currently, we are trying to incorporate a number of physical models or ingredients to go along this path. And I want to tell you somewhat about standard and perhaps less standard ingredients that are used. So first of all, we have to deal with cosmology. And the most simulations currently assume some what we call simple or vanilla lambda CDM model. There are people, of course, that have been working beyond this simple framework, trying to incorporate more dark matter, self-interacting dark matter models, or models with evolving W parameter, or even more exotic models where dark matter and dark energy is coupled. After exploring the cosmological framework of these simulations, we have to go really to the basics. And one of the most fundamental things we have to think about, the fundamental force that drives all structure formation, is actually gravity itself, which is usually done in a Newtonian approximation. This actually turns out to be a fairly good approximation, and the relativistic corrections that some people adopt are usually relevant only very close to very compact objects such as supermassive black holes, or on the scales of the horizon of the universe itself. Obviously, there are alternatives to this, like the modified gravity models, and there is a niche of people working in this area. So the gravity binds together dark matter and baryons, but once we enter into the baryonic physics, a lot of messy processes happen, and this is really what it gives us a major headache when we try to understand galaxy formation. So we have to think about the gas hydrodynamics, which is usually assumed to be an ideal gas, and we have to also think about the dynamics of stars, which are usually considered to be a fluid which is collisionless. Obviously, one can go much beyond these simple ideas, introducing a bunch of transport processes such as conduction, viscosity, magnetic fields, or thinking about stars as real, actually fluid that can interact during stellar collisions, or understanding really the hydrodynamics of stars themselves and stellar interiors or stellar winds that are then distributed into the ISM. Once we start thinking about stars, obviously we have to think about gas thermodynamics. So there we have to think hard about radiative cooling and heating processes, which leads to the condensation of very dense gas into the stars, and we have to think about collapse of this very dense gas into stars or perhaps black holes. So we have to think how these objects form, how do they evolve as a function of cosmic time, and what are all different channels of feedback processes that these objects may impart to their surroundings. Finally, but not the least, reionization is a very important ingredient in understanding the cosmological evolution of structure formation, and that is often assumed to be as a uniform UV background, which is a rather crude assumption. And I want to highlight that actually recently there has been quite some breakthrough in galaxy formation simulations from many different groups that have started to do the full radiative transfer on the fly to understand reionization much more carefully in the early universe and to understand actually the dawn of galaxy formation, which is particularly exciting, for example, because of Al-Magic, WST, and so on. So I want to a little bit summarize what were kind of the achievements that happened in this field, and starting with the basics, and that's what we call the pure dark matter only simulations. So this is where we just discretize gravity and we only incorporate dark matter and we neglect baryons. So this is a kind of, for me, a really striking example. This was one of the first calculations of the sort done by Peebles in 1970, and this is one of the recent simulations where you can see the really extraordinary dynamical range which we can now capture with this type of simulations. And this is quantified a little bit more precisely in this plot taken from Volker Springel, where he's showing the number of particles in a given simulation versus the year of a publication of a paper. And nowadays we have reached the stage where we can do these simulations on accelerated HPC platforms with 8 trillion particles. And this is, in my view, just the start. The field is accelerating, and it will get more exciting and better. However, we have to slightly lean back now and think more hard about the baryons. So baryons are not only direct observable, and this is why we have to understand and model them. They're obviously the fundamental ingredient of any astrophysics. So if you're curious about astrophysics, we have to understand what baryons are doing. But also, if you wouldn't even care about astrophysics and only care about the cosmology, baryons have really significant impact on cosmology as well, given they affect the matter distribution on relatively large scales in terms of contraction or expansion, or changing the shape of structures, or introducing the bias like in the wavelengths in surveys. So understanding baryons is of fundamental importance both for astrophysics and cosmology. So one of the main problems there, it's really the massive physics and multitude of scales where the physics becomes is relevant. And here I would like to stress this: actually there is not a clear cut-off scale where we can say we don't care about the physics we are trying to incorporate. So this is the real kind of big problem that we are facing nowadays. So let me try to illustrate it with this simple sketch. So we want to simulate representative samples of the universe on really large scales, because only having representative samples of galaxies we can meaningfully compare with data, with observations. Otherwise we might have some biased objects or unfair comparisons. Within this vast cosmic web with filaments, and it's not the galaxies, we actually want to understand the galaxy formation itself. So we want to resolve the structures of galaxies themselves. But to understand the structure of galaxies, we actually crucially have to understand the structure of the interstellar medium, because the physics that is happening there determines the properties of galaxies. And that happens typically on the scales of giant molecular clouds, which brings us to much smaller scales than when starting with a fair chunk of the universe. And we know one of the important ingredients in regulating giant molecular clouds is the supernovae, or the winds from massive stars, and that brings us again to prohibitively small scales, reaching 10 to the -6 parsecs. And finally, during the last 20 years or so, there has been really a kind of change in paradigm in understanding that supermassive black holes may be a fundamental ingredient in affecting galaxy properties. but to understand the accretion process onto supermassive black holes and the feedback, either in forms of radiation or jets or winds, we have to go to scales which are even smaller. So just if we would even know all this physics and we would know exactly how to model it, with present-day facilities, this would be computationally unfeasible. So what we have to do is to invoke something that has a really, nowadays, a kind of a bad connotation in the field, but it's an unavoidable truth that all modelers assume, and it is called the subgrid models. So what we are doing there is we are parametrizing the physics below the scales that we can resolve, or we are parametrizing the physics which is too complex to model, this is the other facet of this, with some parameters that may be ill-constrained or completely free, which we try to bound to some reasonable values by observations. So this is a big caveat of this whole field and something that we should bear in mind. So having said that, I want to highlight really quickly, I won't spend too much time on it, on the kind of current state of the art of large-scale cosmological simulations, including baryons and all these physical processes that I talked about, to some level of robustness and accuracy. So there has been a kind of a mini revolution in the field around 2014-15, where several independent groups have managed for the first time to perform large-scale realistic simulations of the universe where they have obtained the simulated galaxy properties that in a broad brush are starting to match the observations for the first time. And I'll show you in a second what I mean by that. And that has been a really healthy thing for the field because people have used different models, they have used different codes, they have used different parameterizations of physics, and they have all made